Okay, today we're going to learn about Ohm's law. And Ohm's law is similar to Newton's laws in that Newton's laws are critical to understand in your study of dynamics and kinematics. Ohm's law is critical to understand how circuits work. So let's take a look and see. We're gonna kind of build up to the law slowly. So we've got a battery hooked up with a light bulb here. And we know that the brightness of the battery is going to change if we change out the brightness of the bulb is going to change if we change out the battery. And we know if we put a 1.5 volt battery in place of the 9 volt battery, we know that the brightness will decrease. Whereas if we put a 12 volt battery in there compared to the 9 volt battery, we know that the brightness would increase. And we know that because the current changes. We know that if we change out and we saw this in our light bulb lab, we know that if we change out this battery, we're going to get more current. So if we have a 1.5 volt battery, we know that the current decreases. And if we put a 12 volt battery, we know that the current is going to increase. Okay, so we can see that the brightness is determined by depends on the current through the bulb. So let's go ahead and put that just so that we kind of keep that in our minds, right? So brightness determined by the current through the bulb. Okay? So we can see, if we ask what type of relationship is there between current and electric potential difference, we can see that there's probably, and you would be right, there's probably a proportional relationship. So if we double the electric potential difference that we can use V to stand for, I think we're ready to use that. So V stands for electric potential difference. We've been using electric potential difference, EPD, but we can use V to stand for electric potential difference as well. So if we double the electric potential difference, the current doubles as well. Okay. Now, we also talked earlier about how electrical components have resistance. And we saw that when we added resistors or light bulbs to the circuit, that the resistance would increase and thereby the current would decrease. So the brightness decreases. Okay, if we increase the resistance in a circuit, we know that the brightness decreases. And we saw this in the demos that we did at the notes the other day. So you could probably guess that if the resistance increases and the brightness decreases, and brightness is determined by current, that there would be an inverse relationship between electric potential difference and current, right? Where current is just represented with I, electric potential difference is still just represented with a V. Sometimes in your reading, you'll see this. You'll see delta V, electric potential difference, delta V. So I'll usually just use V, but you might see delta V as well, okay? Now, so what does this mean? Let's get to an equation. So we can write that current is proportional to electric potential difference. Current is inversely proportional to resistance, and we can combine those two proportions and say that current is proportional to electric potential difference divided by resistance. Now, normally with a proportion, we'd have to put a proportionality constant in there, but it turns out the proportionality constant that we would need, given the units we generally use, would just be 1. So we can go ahead and write then that electric potential difference is equal to current times resistance. So we end up with this equation right here, and that is Ohm's law. We can use this to determine the resistance of various components as long as we know the current through them and the electric potential difference across. So we're going to use this to kind of solve for everything we could ever want to know about a circuit. So let's do a quick review first, and let's take a look at our series circuits, okay? In our series circuit, we know we start with a battery and the electric potential difference of the battery. And we know that if we measure the electrical potential difference across each of the resistors or each of the components in there, that these all have to add up to the battery electric potential difference. So V1 plus V2 plus V3 has to equal the electric potential difference of the battery. Okay. Then we can look at the current through each of the resistors as well. And we know that the current from the battery is going to be exactly the same as the currents through each of these components because they're connected in series. So I through the battery is equal to I1, I2, and I3. That's for a series circuit. That's nothing new. We're just kind of reviewing here, okay? We learned a lot of this in the light bulb lab. Then when we take a look at a parallel circuit, we can see that when we look at the electric potential difference, that the electrical potential difference across each of these components is exactly the same as the electric potential difference across the battery. So the V battery, the electric potential difference of the battery is equal to V1, which equals V2, which equals V3. When we look at the current, we know that the current coming through the battery has to be the total of the whole circuit. So the current through resistor 1 plus the current through resistor 2 plus the current through resistor 3 has to be the total current that is delivered by the battery. Okay, so we're going to use all of this information in addition to Ohm's law, and we're now going to be able to figure out everything we could possibly know about a circuit based on just a couple of measurements. So let's take a look and see how this works. Okay, here we have a simple series circuit, so we can go ahead and circle series, and we know a couple of things based on this, what we're given. So we know at some point somebody measured the current that's through the battery to be 2 amps. Somebody measured R1 to be 3 ohms, and someone measured R2 to be 2 ohms. So the first thing we want to do is we want to plug in the information that we're given. So I know that the current through the battery is 2 amps. I know that R1 is equal to 3 ohms, and I know that R2 is equal to 2 ohms. So that's the information that I'm given. That's just what I know. Now I want to be able to fill in the rest of these boxes with all the information that we could possibly ask for. So, and this is kind of where it's a puzzle. I don't know until I start talking it through what I'm going to fill in next. It won't always be R. It won't always be delta V. It won't always be I. So I have to look at the problem and see, well, what can I do? If anybody does Sudokus, it's kind of like that. You're just looking to see what are you given? What's the next step? So the first thing that I noticed here, because this is a series circuit, is that if the current from the battery is 2 ohms, I know that the current through R1 and R2 also, 2 amps, I know that the current through R1 and the current through R2 also has to be 2 amps. So I can go ahead and fill them in right away. Now something interesting should pop out to you. The interesting thing should be that I know the current and the resistance for both of these components. This is where Ohm's law comes in. This is where I say, oh, well, wait a minute. If I know I and R, I can always find the electric potential difference. So when I look at this, and really when I find any two of the three for the looking across, I know I can find the third. So in this case, since I know I and R, I can find V just by multiplying. So 2 times 3, I must have 6 volts for R1, and I must have 4 volts for R2. So that gets me most of the way that I want to go. Now I have to remember something else about a series circuit. A series circuit, I know that the voltage drops across all of the components connected in series has to equal the voltage drop of the battery. So I know if I have a voltage drop of 6 volts over R1 and 4 volts over R2, that the battery must be supplying 10 volts of electric potential difference. The only thing I'm missing now is the total resistance seen by the battery. So the battery doesn't know how many resistors are ever connected in series or parallel. It just senses the overall resistance. And the way I'm going to calculate that, and you want to be careful, it's going to work out. I don't want to just add these up because that won't always equal the battery resistance. In this case, it will. The only reason I know it will is because I know this delta V and the current through the battery. And since V is I times R, R is equal to V divided by R, which in this case happens to be 5 ohms, which because this is a simple series circuit, it does equate to 3 plus 2 ohms is 5 ohms, but we'll see in the next example that this won't always be the case. This is only a case for a very simple series circuit. So let's take a look now. Let's take a look at our parallel circuit. Okay, we're given some additional information here. So in our parallel circuit now, we're giving that and let's circle that it's parallel, we're given that the battery voltage is 60 volts, so I can go ahead and plug that in right away. We're given that R1 is 10 ohms, we're given that R2 is 20 ohms, and we're given that R3 is 40 ohms. So we can put all of that into our table. And then I have to start using my kind of my knowledge of what happens in a circuit to see what's next, because I can't use Ohm's law anywhere because I don't have enough information in any of these particular rows to be able to fill that in. So I have to look, and the first thing that sticks out in my mind is that if the battery electric potential difference is 60 volts, then the electric potential difference for each of these components must also be 60 volts because they're connected in parallel. So I can go ahead and I can say, well, this must be 60 volts, this must be 60 volts, and this must be 60 volts. Well, now I can go ahead and now I can use Ohm's law because I know the electric potential difference and the resistance for each of the 3 components. So again, if V equals I times R, I must equal V divided by R. So I can do some pretty simple arithmetic here and see that 60 divided by 10, there must be 6 amps flowing through resistor 1. There must be 3 amps flowing through resistor 2. And 60 divided by 40, you might need a calculator, or you might see that that's just 1.5 amps flowing through resistor 3. So now I know the resistance, the electric potential difference, and the current through all 3 of my components. The only thing that's left to do is figure out the current and the current from the battery and the resistance that the battery sees, the overall total resistance. So let's see, let's figure out the current first. If there's 6 amps through R1, 3 amps through R2, and 1.5 amps through R3, I know that the total current that the battery must deliver must be 10.5 amps. Right? Because when I look back at my current rules for a parallel circuit, I know that the battery delivers the currents added up through each of the components. Now I can use that V equals IR, so R must equal V over I for the battery. And I'll see that 60 divided by 10.5 certainly isn't 40 plus 20 plus 10. If I put that in your calculator, you should see that it's 5.7 ohms. So this is how I want to get the resistance of for my battery, the resistance that the battery sees. Otherwise, I will get the wrong answer for the resistance there. Okay? That's it. That's the big benefit of Ohm's law. We're going to get some practice problems on those in a document. If you need to rewatch these notes to see how I did these problems a little bit slower, I would suggest that. Otherwise, have a great day.